We'll be working with the same couple definitions of upper bound and least upper bound that we already had, but we'll be having one more definition of a maximum here. And we're going to start with, give an example of a finite subset of R that has a least upper bound, and identify both its least upper bound and its maximum element. And so I just made an arbitrary little finite set here, 2, 3, 7/2, 15/4, 31/8. And in this case, the least upper bound equals the maximum, which equals 31/8. And the second question here says, show that the open interval from 0 to 2 does not have a maximum. And to do that, I did a little proof by contradiction down here, and started by saying that m is the maximum of 0, 2. So we want to assume that and then find a contradiction within that. And so I said that there's an arbitrary value x that is within our open interval 0 to 2, and that x is the average of our maximum value in that upper bound of 2. And so that means that x is between 1 and 2 because our m is between 0 and 2. And x minus m in this case would be m plus 2 over 2 minus m. And we can use algebra to simplify this into x minus m equals 2 minus m over 2. And since our m is going to be greater than 0, we know that 2 minus 2 over 2 is going to be greater than 0, which means that the difference between x and m is positive. And since that means that x is greater than m, and that means that there is no max on our open interval from 0 to 2, because we found a contradiction there. And the third question here asks, let x1, x2 to xn be within R, and let n be within the natural numbers, excuse me. Sn is x1 to xn. And we're going to prove using mathematical induction on n that Sn has a maximum element, which is 1 of x1 to xn. And for induction here, we want our base case. So S1 is going to equal x1. And since x1 is the only thing within our set, and it's equal to itself, there's no other values that can be greater than it, it's going to be our maximum. And so Sn is going to be x1 to xn, and we're just going to say m is our max. And so here's Sn plus 1, and I just replaced all of, or substituted all of x1 through xn here with our value of m, because we know that if m is our maximum of Sn, then there's no other values larger than m in that set. And so now we have Sn plus 1 equals m and xn plus 1. And so we know that the max of Sn plus 1 equals m, or it equals xn plus 1. And this is because either m is greater than xn plus 1, equal to xn plus 1, or less than xn plus 1. And so either m or xn plus 1 has to be our maximum of our finite set. So Sn plus 1 does have a maximum. All right, thank you for watching.